These are notes 1.1 on measurements, and in your book, this is going to be pages 66 through 77, and in your study guide, pages 8 through 11. All right, so for these notes, we have some objectives here. So if you want to pause and write these down, and then once you get them written down, you can start again. So you're going to appropriately read and report a measurement with one estimated digit. So by the end of this video, you should be able to do all these. Identify a number as an exact number or a measurement. Explain the difference between accuracy and precision. Identify which digits in a measurement are significant. Write a number in both scientific notation and standard notation, and calculate math operations and round the answer with the correct number of significant digits. So measurements versus exact numbers, what's the difference between those? First of all, pause and write the definition of exact numbers. All right, exact numbers can be counted. These are numbers that when you go to a restaurant, it's the number of people in your party. That's an example of an exact number. You can count 5 people, 4 people, 3. Another example would be 8 eggs in a carton. So what other examples can you think of? Maybe how many pennies are in a piggy bank? Things like that, stuff that you can exactly count. Measurements, so pause and write down the definition of measured numbers. Measured numbers are numbers that it's an estimated amount and they're measured using equipment, and then they're rounded to a certain number of what we call significant digits. And measured numbers are only as specific as the equipment that's being used, like measuring the length of a pencil. So here we have 2 examples. We have 2 pencils and we have 2 rulers. And you can see on the first ruler that the measurements, the hash marks, start at 0, and then it goes 1, 2, 3, 4, 5, 6, 7, 8. There's no tiny marks in between each of those whole numbers. But on the ruler that's on the bottom, you can see the hash marks there between each number. So the pencil can be measured more accurately by using the bottom ruler. So I'll write this down. Always, always, always estimate 1 digit past the accuracy of the measuring device. So pause here so you can write that down. All right, so if we measured the pencil on the top, what is the certain? You have to look at the certain digit, and then you have to estimate 1 digit after that. So what do we know for absolute certain? Well, that the pencil is at least 5 centimeters long, because we see the tip of the pencil goes to at least the 5 mark. But it falls somewhere between the 5 and the 6, and we don't know exactly where that is because we don't have any hash marks. So we're going to have to estimate where that is. So we're estimating here that it's a little less than half. So that's going to be our 0.4 right here. So the measurement for this top pencil is 5.4 centimeters. The 5 is the certain digit, and the 4 is the estimated digit. Now let's look at the bottom ruler. Well, since the bottom ruler has hash marks in between the whole numbers, we see that the pencil goes to at least 5.4. Those are 2 certain digits that we know of, but it falls somewhere between this hash mark and this hash mark. So we're going to estimate that it's almost to this big heavy hash mark. So 5.4 is our certain digit, and then 9 would be our estimated digit. So again, always 1 estimated digit past the accuracy of the measuring device. All right, so now the definitions of precision and accuracy. So pause and write these down. All right, precision. Precision is defined as the consistency in the measurements. Now, consistency, what does that mean? That means how close your answer is to other answers that other people have taken. So in consistency, you have to have more than one measurement. In accuracy, it's the correctness in the measurement. So if I were to ask you how many eggs are in a dozen, you can tell me 12 and you would be correct. So you can be accurate. But could you be precise? And the answer to that is no, because I only asked you. Now, if I asked everybody in the classroom and everybody gave me the answer of 12, then you could also be precise. So we have a statement here. You can only have blank when more than one measurement is made. So can you fill in the blank? And the answer to that would be precision. Because remember, precision is the consistency in the measurements. Your measurement is compared with other people who made the same measurement. So many times what they use for this example is a target here. So accurate, you always want to hit the target in the bullseye in the center. So if you throw darts and you've thrown 7 darts here, you can see that all 7 of these landed somewhere around the bullseye, either in or touching the bullseye. So that would be accurate. This is an example of precision. Well, we threw the dart, but all 7 times they landed here on the white and the black ring. So that's not very accurate, but they're all really, really close to the same spot. So that would be precision. Accuracy and precision is where they're really close and they're in the correct spot. Okay, so if you need to pause and go back and look at these and let that sink in, please do that. All right, so let's take measurements for this pencil. So what is going to be your certain digit? Well, your certain digit is a 0. That's what we know for certain because there's no marks between the 0 and the 8. So we're going to have to estimate somewhere between the 0 and the 8. So look at where the halfway mark would be. Is it past the halfway mark? I would say yes. So the measurement for this pencil is going to be, I would say 6. Okay, so 0, we can go ahead and put the 0 there just for learning's sake. But when we have a 0 in front of a number, we usually drop it. So the 0 is the certain number, and the 6 is going to be the estimated number. So on this next one, what do we know for sure is the certain number? Well, we know for sure the certain number is 5. But the pencil tip falls somewhere between 5 and 6. So 5 is our certain number. So our estimated number is going to have to be somewhere in between that. Let's just say 5. So we have a certain and an estimated. Now in this last example, what do we know for certain? That the pencil is 5.4. We know that for certain. But it almost goes to the halfway mark. So let's say 9. So 5.4 is our certain. That 9 is going to be the estimated digit. All right, and for our final topic, we're going to talk about significant figures. These are very important when you're in math and science. So pause this and write this down. Significant figures are also called significant digits or sig figs. Sig figs tell us the accuracy of a number, how accurate the number is. These 4 rules, you need to know these because as we're working with numbers in chemistry, you're always going to put your answer that you report for your homework or for a test in the correct number of significant digits. So all non-zero numbers are significant. That means 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are significant digits automatically. Leading zeros are never significant. So if you have a number like 0.01, those zeros are leading. That means they're beginning the number. They're in the left of a non-zero number. So those numbers are never significant. The third rule is sandwiched zeros are always significant. So if you have a number like 504, the 5 is going to be significant because it's a non-zero number. The 4 is going to be significant because it's a non-zero number. But the 0 that's sandwiched in between is not, always. So it will be significant because it's in between. So 504 has 3 significant digits. And then lastly, trailing zeros are only significant when there is a decimal. So if I have 50400, those last 2 zeros are not significant. But if I say 50400 and then I put a decimal there, then that decimal makes those zeros at the end significant. So some examples here. How many significant digits are in 2.53? Okay, so those are all non-zero numbers. That's rule number 1. So there's going to be 3 significant digits there. Okay, how about 0.00241? So go ahead and after each one of these, pause so that you can check back with the rules, and then you can start the video again and see if you got the answer correctly. So the answer there is 3 significant digits. The 3 zeros in the beginning are leading zeros, so you would not count those as significant. What about 1.00? That's 3 significant digits. Because it has a decimal in it, those trailing zeros become significant. 2400. That's 2 significant digits. There are zeros at the end, but there is no decimal, so those do not count as significant digits. So that has 2 significant digits. 0.01020. So we have zeros all over the place here. This is going to be 4 significant digits. Now the 2 zeros at the beginning do not count. Then we have a 0 sandwiched between the 1 and the 2. That does count because it's a sandwich 0. Then we have a 0 at the end that's going to count because look at the number. There's a decimal in that number. The decimal can be anywhere. It doesn't have to be at the end. It can be at the beginning or in the middle. Okay, so that 0 on the end is going to count as significant. 320 with a decimal there. That's 3 significant digits. That 0 at the end is going to count because of the decimal. Okay, that's a big long number. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 significant digits here because all of these zeros at the end are not going to count because there's no decimal in the number. All right, one thing that I want to say here, I'm going to go back. Significant digits. One thing that I'm going to say here is this is one of the concepts that we're going to use all year long. So please, it's very important that you learn how to count significant digits, learn these rules, learn how to apply them, because again, this is something we're going to use all year long. Chemistry is very math intensive. So we're going to be doing a lot of math in here, a lot of multiplying, dividing, adding, and subtracting. So if you learn these rules and learn how to do this, it's just going to make the other things easier. Okay, back to multiplying and dividing. As I mentioned, there are 2 separate rules when you multiply and divide and when you add and subtract. So we're going to cover multiply and divide first. When you have a series of numbers that you're multiplying or dividing, the rule is you round to the least number of significant figures that are in your data. So here we have a set of data. We have 5 numbers we're multiplying. So when you multiply these out on your calculator, it's going to give you an answer of 55.34 62976. If you were going to report this answer, it would be reported as 55. Okay, so why? Why is that? Well, we're going to count the significant digits in each one of our data set, our given data. That's all you count the significant figures in. When we start doing these chemistry problems, we're going to talk about the significant digits in the data. But here we have 5 different data sets. So we're going to count the significant digits in each one of these. So in 3.2, there are 2 significant digits. 2.35, there are 3 significant digits. 3.89, there are 3 significant digits. 1.892, there are 4 significant digits. In 1.0, there's 2 significant digits. Now, this is the only number that contains a 0. Okay, so the rule, the 0 is at the end of the number, so it's a trailing 0. Is it significant? Do you see a decimal? Yes, there is a decimal there. Therefore, that trailing 0 is counted as a significant digit. So this one has 2 significant digits. So we're going to look at all those, and we're going to find the least number that's given in the data. Well, that is 2. So we're going to look at the number that's on our calculator, and we're going to round this to 2 significant digits. Well, start at the left. This first 5 here is your first significant digit. The second 5 here is the second significant digit. That's 2 significant digits. So you're always going to look at this next digit to see if you're going to round the digit before it. So this is a 3. The rule on rounding is if it's less than 5, we're not going to round it. If it's 5 or more, we are going to round it. So since this is a 3, it's not going to round this 5. So our answer is 55. So that's multiplying and dividing. The rule for addition and subtraction is round to the least number of decimal places that are in the data. Okay, so if we add all these up, we're going to get 12.332. What's the least amount of places? It's 1 number past the digit. So we're going to round this to 12.3. Okay. So we're going to look at the second 3 here, second 3, to see if we're going to round this first 3. And of course, since it's a 3, we don't. So that's why our answer is 12.3. Most of the math that we're going to be doing in chemistry is multiplying and dividing. Occasionally, we'll use the addition subtraction rule. So make sure you're clear on that. All right, and so for our last topic that we need to talk about in our notes is scientific notation. So go ahead and pause the video and write this down, and then we'll come back and we'll talk about it. All right, scientific notation. What is scientific notation? Scientific notation is a way of writing a very small or a very large number that makes it manageable. So if we have 602-214-129-270-000-000-000-000, that's 602 sectillion. That's how you say that number. That is a huge number, a very, very large number. So in order to make that more manageable, more easily put into the calculator, more understandable, we're going to make that scientific notation. So the way we do that is we take and we move the decimal until it's behind the first whole number. So here we're going to move the decimal until it's after the 6, the first 6 there. So it's going to be 6.02. And then we're going to count how many times did we have to move the decimal to get it to that spot. We're going to have to move it 23 times. So it's 6.02 times 10 to the 23rd power. So that's how you would convert that to scientific notation. The number below that, 0.00000000001, is a very, very small number. To help us out, we're going to convert that into scientific notation. So we're going to move the decimal until it's after the first whole number, which is going to be the 1. So it's going to be 1.0. How many times did we have to move the decimal to get it there? 23 times. Okay, so what's the difference in this positive 23 and this negative 23? If you're moving your decimal to the left, it's going to be a positive number, the exponent. If you're having to move the decimal to the right, it's going to be a negative exponent. Okay? Another way to think about this is the hint. If the exponent is positive, it's a number that's larger than 1. So in this first example, 602 sextillion, that is a number larger than 1, so your exponent for your scientific notation is going to be a positive number. But the second number where you have your 0.0000, that's a very, very small number, less than 1. So the exponent is going to be a negative number. We see negative 23 there. All right, so there's no set standard for when to use a number in scientific notation. It's just a method to save you time so that you don't have to continuously write out all of those zeros, all of that big long number. But I would like you to use scientific notation anytime the number is in the millionth place or beyond. All right, so let's look at some examples here. This first example, we have 2.54 times 10 to the second power. Well, that's a positive exponent. So we're going to be moving our decimal when we convert this over into a standard notation. So this is scientific notation. This is what we call standard notation, which is just like a regular number. So we're going to move the decimal 2 places. So when we move it 2 places, it's going to be behind the 4, 254. Okay. All right. So 2.34 times 10 to the negative 2. That negative exponent tells us it's going to be a number less than 1. So we're going to move our decimal to the left to change it over to standard notation. So when we move it 2 times, we're going to get 0.0234. All right. So for our third one, we have 1,344. If we're going to write that into scientific notation, that's a number larger than 1. We're going to move our decimal to the left, so it's between the 1 and the 3. Remember, we move the decimal until it's after the first whole number. So we're going to move it till it's between the 1 and the 3. Okay, so it's going to be 1.344 times 10 to the, how many times do we move the decimal to get it in that spot? We had to move it 3 times, so the exponent is going to be 3. And then for our last example, we have 0.319. That's the same thing as 3.19, so we're moving our decimal till it's behind the 3. How many times do we have to move the decimal? 1 time. Now, is that 0.319 a number larger than 1 or smaller than 1? It's less than 1, so our exponent's going to be negative. We're moving the decimal to the right, so that's a negative exponent. So that's going to be 3.19 times 10 to the negative 1. Okay, so I want you to take these 5 numbers that are written here, and I want you to write them in scientific notation and just round all of your answers to 2 significant digits. 2 significant digits. So go ahead and pause the video, write those down, and see if you can write those, convert those into scientific notation, and let's look at the answers. All right, so for the first one, 12,854. So how do you write that in scientific notation? 1.3 times 10 to the 4th. Okay, so why 1.3? Well, if we move our decimal to right here between the 1 and the 2, okay, that's going to be 1, 2, 3, 4 times, so it's 10 to the 4th. But if we look, it says round all of your answers to 2 significant digits. So the 1 is your first significant digit, the 2 is your second significant digit. So we're going to look at this 8 to see if we're going to round the 2. Now remember what I said a while ago, 5 or more, you're going to round it up. So that 8 is going to round that to a 3, so it's 1.3 times 10 to the 4th. Now if you need to pause this video and go back and recheck the other 4, correct your answer Now that we've talked about rounding, and we saw an example where you do round a number up, do that. All right, so we're back. 0.000225. So this is going to be 2.3 times 10 to the negative 4. Okay, the next one, 4.4 times 10 to the 10. Now this is a number larger than 1, so your exponent is positive. We move the decimal 10 times to get it between the 4 and the 3. This number is an 8 after the second significant digit, so that's going to round that to 4.4. Okay. 4.3 times 10 to the negative 6th. And finally, this is a tricky one, 5.3 times 10 to the 0 power. All right, so let's talk about that for a second. Well, the decimal is already where it needs to be. Because remember, we're moving our decimal till it's after the first whole number where we didn't have to move it. So 5.3, we only want 2 significant digits, so we're going to drop off that last 0. Times 10 to the 0 power. We didn't have to move our decimal, so to the 0 power. Because 10 to the 0 power is 1. 1 times any number is itself. So that's how you would write it in scientific notation. It really doesn't make sense to rewrite this number in scientific notation. It's just a rule. Okay, so that does it for this video. This next slide here is about calculator use, and we're going to talk about this in class. We're going to talk about how to enter these numbers into your calculator using your Casio or your Texas Instruments calculator. So what you need to do is make sure that you bring your calculator to class tomorrow, because we are going to be talking about this, and you need to know how to use your calculator